Let's take a detour. Enter maths, right? So forget about everything that we did about regularization and all of that. We will do one simple thing. Imagine a circle. Circle. What is the equation of a circle? Equation of a circle is
x square plus y square equal to r square.
That is right. Let me just write it like this in simple.
Is this in 2 space or 3 space?
I'm just looking at two space for the time being.
Okay.
You can do it in 3 space. It doesn't matter, but let's be very, very simple. Gx, equation of the circle is x square plus y square is equal to some constant. Constant. Let me call this constant r. Well, it is r squared, but let me just say r squared, right? Which is basically the radius of the circle, right? So what happens is that different circles will have different radius, isn't it? That's all it is. All you're saying is all points which are at the same distance from the center define a circle. They define this. Now let's do this. Let's look at this equation and take its derivatives. So we will do, now you notice that this is an equation in 2 dimensions. So how would you take derivatives? You can say that, hey, what happens to G if I just keep y constant and just change x? So if y is constant, the derivative of G, which is with respect only to x, holding y constant would be what? 2x. Derivative of G with respect to y would be 2y.
So is it about the direction, like where the direction?
No, hold on, guys. Just pay attention. Don't jump. Is this pretty obvious? Partial derivative means you keep the other variables constant and you take the derivative. This. Now the definition by definition, gradient, right? So take a point. Let's take a point, some particular point. I'll just take a point x, y, right? Or maybe some special point xa, ya. It doesn't matter. Actually, let me not clutter it with notation. So just assume that some point P is this. Are we together? What is a point? A point is a vector P. Would you, that part is also obvious. This is the P vector and this is the point P. So a point and a vector are the same thing, right? This is one of the simple intuitions to remember. And now, so this point, we can write it in a sort of notation. Point, we can write it as P is equal to, in high school notation, you would probably write it as xi plus yj. Isn't it? There's an x component to it and there's a y component to it. So far, so good, right? We could also write it, but in a more sort of a formal notation, we write it as a column vector. People typically write it as xy. There's no difference between these two. They're just different styles of writing the same information. In machine learning community, we tend to write vectors as columns. Column vectors. The first component, the second components, we vertically stack them. Why is this a good idea? See, if you use ijk, right, then what happens after you reach z and you have more features? You run out of indices, isn't it? You have to cook up newer and newer indices. It's just simpler to use a simple notation. Forget about ijk, isn't it? And then if there are too many of them, you can put dot, dot, dot in between. Right. So for example, if it was n dimension where n was 30, you could say x1, x2, and then xn. Right? Assuming there's a column, a stack of all those component numbers. That's why in machine learning, we use this notation. Now look at the gradient. This gradient is defined. Gradient of G is here, is defined by definition is gradient. Are we together? Now, let me use a color for gradient, a different color. I will deliberately use gradient of G. It's a vector. It is this. It is the definition. It is that vector which is made up of the partial derivatives of that, right? So now in this particular example, let us go back and compute our G x y is equal to x square plus y square is equal to some constant square. Gradient of G xy is equal to what? It is equal to 2x. Again, I'll just repeat the whole thing from here. Gradient of G x and gradient of G with respect to y. It is this vector by definition, almost by definition here. And this is equal to what? A 2x, 2y. Now, this is an interesting thing. In this special case, in this case of
It should be y by x, right? Yeah.
y. What do you mean by yx?
Because the gradient is a slope, right? The slope here for the p would be y divided by x, right? The circle that you have.
No. See, this is it. This is the definition of gradient.
Okay.
This is the definition of gradient. Right? So it is this. Are we together, guys? So you agree with this? I have not done anything so far. I have taken the definition and applied it to this particular circle as a constraint surface. And now you notice, now, what is P? P is just xy. It is the point xy, isn't it? So is there a relationship between the gradient and the point? For the circle.
Yes.
Yes, for the circle, gradient G happens to be is equal to 2 times the x vector, the p vector itself. Does this make sense? In this particular case, if you look at the value, and so it is equal to 2 times xy. Right, which is equal to 2 times the p vector. Do you see the connection here, guys? So you say, well, in the case of a circle, there is something interesting. Let me show what it means geometrically. If p vector is this, therefore, what is the vector for G? G is essentially the same vector at twice the length. This is grad G. Would you agree? Isn't it? And that is a crucial insight. What we are saying is, so let me summarize the point. So we find for this special case, I wouldn't use the word special, for this specific case, grad G points in along P, right? So let's not worry about a factor of 2 and so on and so forth. Right? So magnitude we are going to ignore. It points in that direction. But more crucial than that, and is perpendicular to the tangent of the circle at P. Would you agree with this statement? This is a statement that is perpendicular. Let's see if this is true. I just made a big statement. I'm saying that this blue line gradient is perpendicular to the circle, perpendicular to the tangent of the circle. What is the tangent?
line that will go across the P on the circle.
This is the tangent at P. Would you agree?
Yes.
The green line is the tangent. And what is grad G doing? It is perpendicular to the tangent. So far, so good. And this will always be true for any other circle that you draw. If you do another constrained surface, the same reasoning will remain true. Right? So now, without showing this, because it gets into calculus, I'm using this very simple example to make a statement, which I'll make in a moment. Now, notice that first it is perpendicular to the circle. What is the circle? Circle is the contour. Like, it is the point at which r squared, the constant, remains the same, isn't it? So it is perpendicular to that. Now, if I want to go in the direction of maximum increase of value of G, so suppose I take a point, let's take a point, one more color is called for. Let us take a point, this point Q. At Q, if I go in this direction, parallel to this contour surfaces, let me draw one more contour surface here. So if I go along the curve, is G increasing or decreasing?
Unchanged.
Unchanged. It remains the same if you go tangential to the constraint surface. On the other hand, if I want to go in the direction where it increases most, what about going in this direction? Is that the best way that I can do? Go in any arbitrary path, but slightly move outwards, isn't it? You're increasing your G. But what is the way to increase G? So suppose you are allowed to make only 2 steps, right? You said, in all of our stories, there's always, in all mythologies, there's a story that somebody is asked to take only 1 step, and whatever he can cover or she can cover in 1 step belongs to the person, right? So suppose you had to take a 1 such step, and you want to increase your G as much as possible. In which possible direction would you move your G?
Perpendicular to the tangent.
Perpendicular to the tangent, exactly. So you would want to go in the direction, this direction, at Q. Grad G at the point Q, whatever it is, that direction you already realize is perpendicular to the surface. So the path of greatest increase in G, and that is the intuition, the path of, I'll write the point inside. The path of fastest increase of G xy is perpendicular, and we won't use the word perpendicular. The word people often use is normal, because perpendicular is with respect to line. When you go perpendicular to the surface, the wording, it means exactly the same thing, but people use the word normal to the some r square, some constant surface. Here it is a line, it's a curve, but imagine that it's in higher dimension, it would be a sphere, perpendicular to the sphere. Where's my sphere gone? Okay, it's somewhere. Oh, there it is. So imagine it would be the line from the center of the earth penetrating straight up to the sky, isn't it? So this is a very interesting fact. And now I will generalize. I'm going to say that whenever you get any kind of a complicated surface, what is true of a circle or a sphere is true of ellipse and ellipsoids, right? Because locally an ellipse or an ellipsoid looks like a circle. You wouldn't know whether it's part of a circle or an ellipse, isn't it? So it's true for ellipse, but it is actually, surprisingly, this statement is universally true, right? Grad G will always point orthonormal or like normal to the constrained surface. Are we together? Well, that is very good. And it is also the direction of most increase and represents direction of greatest increase in G. This is our key result that is true. However complicated your surface is, like, it will still be true. At this particular point, right? So if you have a lot of surfaces like this, I don't know, at this point, it will still be the gradient, right? A gradient would be the direction of maximum increase, and it will be perpendicular to the contour surface, constrained surface. Now, with that digression in mind, now comes the key thought. So far, are you folks with me? Right? I hope what I said was simple mathematics, but this mathematics has far-reaching consequence. Now, with this mathematics, come here. Look at the red circle and one of the contour lines, right? The contour line being whichever one it was, that P, the contour line P. So what can you say at the point at which the contour line has some, the yellow lines are error lines, right? Error surfaces, curves of constant error, isn't it? The yellow lines, let us notice this. The yellow lines, well, not lines, yellow curves are equi-error curves, right? Curves, surfaces, more generally. B, red line red curve, red circle is the constrained surface. Right? So G of beta is this, and this yellow one are the error associated with the beta at that particular point, isn't it? The error associated with that. At this particular point, we can tell what the error is because it's a point in the hypothesis space, and we can also compute the value of G. Does that make sense, guys? Right? Now, what do you say? When these two surfaces just tangentially touch each other, think about it. Where is the gradient of, at this point, P, where is the gradient of the red circle pointing? This way. So this is gradient of G, right? And in which direction is the gradient of the error surface pointing? Towards the opposite direction. Let me just mark it as big bold. So would you agree? This is gradient of the error surface. This is the direction. We'll ignore the magnitude. Let's not worry too much about how much big one is compared to the other, right? But the directions are opposite, isn't it? If two vectors have opposite directions, what can you say about them? Would it be fair to say that the gradient of E of the error surface at that point is equal to, up to a proportionality constant, because magnitudes will be whatnot, up to a proportionality constant, the same as gradient of G with a minus sign. Why minus sign? Because if you put a minus sign, then you can be sure that lambda is positive. Right? You can give positive values to lambda. So would you agree that this equation captures our discovery? Because here, when we look at it, this is gradient of G, and this is gradient of E, isn't it? So this equation holds true. Would we say that, guys? Ask me questions, guys. Stop me here, because this is a very, very crucial point. Do we agree?
I have a quick question.
Yes.
So in the inside, you mentioned the path of fastest increase. What exactly does that mean in this context?
In this means, if you have a circle, what is the constraint? It is R, the radius, right? Square of the radius. What is the fastest way to increase this? Go outwards.
Oh, I
Go
see.
radially outwards. That is the path of greatest increase of radius, isn't it? How do you increase the, you are at a point, you want to increase the radius, just go out, isn't it? Radially outwards.
Yeah.
Sonal? What is the point? I mean, why do we have a constraint surface? Okay, just say that we don't want our betas, the parameters, to become big. So we say that we will stay tightly close to small values of beta. So small values of beta, we're saying I have a budget. None of the betas can be more than, let's say, some constant, right? So what happens? It puts you in a circle, isn't it? Because the sum squared values of all the betas must be less than some constant. You're saying within the circle, you're close to the origin, so all the values of betas are small, and that's what we want. We don't want to go out. Always around the origin, because you want to make it small, right? Small means that's all. Yes.
So when you say the constraint, right? Like, but the whole point is to use the gradient descent and reduce the errors. So
No. Gradient descent has already found for you this nice parabola, and it has found this the true optimal beta star, and it has made this nice other equi-error surfaces, A, B, C, D, E, F, G. So your learning is over now.
Oh, okay, so this is after the learning.
After the learning. Yes.
Where is our optimal point where you can say that?
Yes, exactly. So you've already discovered your bowl. You built it. You know where its absolute minima is. Now you're saying, well, you know what? We are not going to go that. We want to be just close to it, not go to that best beta star, because we know that in reality it's not really the best, right? It leads to wild oscillations. It doesn't work for test data. It only works with training data because it has gone and fit to the noise.
So Asif, how do we know that constant? So it's relative, right? So how big?
Yes.
By looking at the residual plot or something like that?
Yeah, we will learn about that. Hold that thought in your mind. I haven't told you how that constant comes about. But at this moment, guys, what I have done is, without this little mathematical digression, has taught you not just this, what is very relevant to regularization, has actually taught you one of the deepest or hardest themes typically people face in college calculus, called constraint optimization. What you have just learned is the calculus of constraint optimization. This lambda in calculus has a name. This is the famous Lagrange, oh my goodness, I will massacre the name. Lagrange, I hope it is Lagrange multiplier. It is the famous Lagrange multiplier. And what this equation says, I will rewrite this equation here. The equation we came up to is that the gradient of some function E is equal to minus, in this particular case, obviously, I made it very real with respect to this, but it is a general truth in mathematics. When you have a constraint and you want to find the minimize E, given this constraint. So in other words, find a point at which E is as small as it can be, but it cannot violate the constraint. You cannot go out of the circle. This equation is called the Lagrange, this is called the Lagrange multiplier. Lagrange multiplier. Lagrange multiplier. Now this equation, I'll write it in a slightly different way. And now the rest of it is just thing. A plus lambda gradient of G is equal to 0. Can I just rewrite it like this? Right. And now with both with this, from this we can conclude that gradient of E plus lambda G is equal to 0. So what are we trying to do? So we are trying to minimize, let me just call it L, right? You're trying to minimize not just the total error, but another function, loss. It's called the word loss. And thus we get introduced to the big concept of loss in machine learning, the loss function. L is your loss function. What you're doing is you're minimizing not E, but the sum total of E plus lambda G. Are we together? Right? So hold your thoughts, guys. Let me tell you some of the consequences. And so these two have opposite effects. If you minimize just only E, you'll go far from the origin. Then what will happen to G? You will have to have a pretty large constraint surface going all the way out to that point, isn't it? So G will increase. So if you try to minimize E only, then your solutions that you'll get will be at large G. You don't want that. So they have opposite effects. So you have to be careful. You want to keep G small and you want to keep E small. And you have to bring them both down while both are competing. They're pushing each other out, right? That is the constraint optimization. Now, let me write it down, this loss. Once you understand, so now if you realize what I did is I use this problem of machine learning, loss surface, and error surface and constraints to introduce you to actually a powerful idea of constraint optimization in calculus. So once you understand this idea, for the rest of all the discussions that we'll do in machine learning class, I'll assume that you understand constraint optimization, right? Because we'll reuse this idea at many, many places. Here, we will write loss is equal to E plus lambda G, right? Then in the case of regression, remember what this is, or let me just say regression. In the case of regression, this is what? E is the sum squared error, yi minus yi hat squared, isn't it? You can take sum squared error, you can take mean squared error, it doesn't matter. You can take this, or you can take 1 over n, doesn't matter. Am I together, guys? It is the same thing. Error is error, right? You may or may not take this. So I will skip this. I will just skip this quantity plus lambda. Now, what was G? Remember, the G was not in the real space. G was actually in the beta space. It was beta naught square plus beta 1 square, because where was the circle being made? In the hypothesis space. Do you see this, guys? This is the hypothesis space. In the hypothesis space, equation is in terms of betas, right? So this is true. Let's bring it here. So this is equal to beta naught square plus beta 1 square, right? So people often write this equation as square plus lambda summation of beta j square, right? J being the number of parameters, j is equal to 1. And suppose the model has p parameters, right? Whereas this I is equal to n, number of data points. This summation is over data set. This summation over parameters of the model. And this is therefore the celebrated equation of the famous equation of L2 regularization, or RIG. It is called regularization, or most often when people say they're regularizing, this is by default the regularization that people use, right? This is the famous equation, right? You must remember this, and your book will talk about. Now, what happens is most of the books, in fact, don't explain how you arrive at this. They just give you this equation as a fact that regularization is to minimize this loss equation. And if you do this, then you won't have oscillations. Your parameters won't become large. They don't actually, I mean, sometimes they do, but most of the times the books that I've seen, they don't tend to explain. So I have taken you through an intellectual journey in which we have tried to understand how this equation, excuse me, I apologize. I need water, guys, so we'll take a break after this. Yeah.
So Asif, one quick question I have. So equation that you have beta j, where j equal to 1 to p. But the one that you have is a beta 0 to beta 1 plus beta 2. So intercept is not the part of that?
Sorry, let me make it 0. Better. Good. So they are a p plus 1. You're right. Like, that is good. So what it does is we have this famous equation now of, and we went through the intellectual journey of understanding it. I will just recap this journey and then we'll take a break. So this journey basically says that, see, if you do unregularized, or now the word ordinary, you must have seen this word in literature. The regression, linear regression that we learned is called OLS, ordinary least squares regression. Why ordinary least square regression? Because the loss function is the same as the error function, the sum squared error function. It does not contain the other term. When you do put the other term, it is regularized regression. So what we were doing till now was ordinary least square regression, namely unregularized regression. Are we together? Right. This is an important point, and we have gone through the journey. It's a very simple journey. It basically says, hey, if you are not careful, your parameters will blow up. How do you prevent it from blowing up? You put a circle around the origin and say, no matter what, I'm not going to go out of it. The learning must tell me the best value, the minimum error point within my circle. So which of these points that I have within my little disk here, a sphere here, which of these has the least error? And whatever that answer is, I'll consider the right answer, not the absolute sum squared error minima, the bottom of the error surface board. So you change the loss function itself, and this is where you stop, right? So with that thought, let us now take a little break for about 10 minutes.